Many global education frameworks are built on the assumption that students arrive in the classroom as blank slates. The curriculum is designed as if learners bring zero prior knowledge to complex scientific subjects. Testing that assumption requires looking at the island communities of South Sulawesi, Indonesia. In these dense archipelagos, the primary geographic reality is a persistent scarcity of freshwater. For these students, water conservation is a physical daily routine of survival, requiring grueling manual labor just to maintain a household supply. Standardized STEM modules on saving water are often written for students who have never experienced water insecurity, focusing on vocabulary and concepts that feel distant from this reality. This creates a disconnect between the classroom and the home, as teachers try to introduce basic conservation concepts to children who are already practical experts in managing a limited resource. In 2026, researcher Sundari Hamid and her team began documenting this disconnect by measuring the baseline ecological awareness of secondary students across the region. The initial data followed a predictable pattern. When tested on renewable energy and waste management, students' scores sought in the moderate to low range. But look at water conservation. This column indicates a significant deviation, revealing a baseline awareness that far exceeded other domains. The researchers identified this as a specialized cultural asset, a deep, existing knowledge base cultivated by the constraints of their environment. This forced a redesign of the instructional approach. The goal was no longer to teach a new behavior, but to find a way to engage students who already possessed the practical answers. Effectively educating these students meant moving away from generic instruction and toward a model that could scientifically validate their existing lived experiences. The team developed the traditional water filtration technology project, an Ethno-STEM module that merges community wisdom with rigorous inquiry. Instead of using imported, pre-made kits, the project requires students to build filtration systems using the same materials their ancestors relied on for generations. In the first phase, students apply mathematics to calculate fluid flow rates as water moves through local materials like palm fiber, sand, and charcoal. They then deconstruct the physics of the system, identifying how the specific texture and density of these local materials create physical barriers for different types of sediment. Finally, students use modern chemical testing to analyze the purity of the output, comparing the results of their ancestral technology against modern safety standards. This process turns a traditional community craft into a sophisticated engineering challenge. By the end of the project, the students haven't just memorized a textbook. They have used the scientific method to prove exactly why their ancestors' survival technology works. This approach is part of a broader framework called ethnopedagogy, which positions local culture as a legitimate source of scientific insight. When the curriculum validates community wisdom as a scientific asset, it provides an academic foundation for knowledge that was previously seen as mere folklore. This integration allows students to see their identity as community members and their identity as scientific practitioners as one and the same. During project showcases, researchers have observed students confidently explaining their technical filtration data to village elders and parents, demonstrating a clear shift in cultural pride and academic self-assurance. Because the science is now grounded in their own personal history, the commitment to local environmental conservation becomes a matter of preserving their own heritage. The most effective way to prepare the next generation for global environmental challenges is not by ignoring their past, but by giving them the scientific tools to empower the wisdom of their ancestors.